Now put the display of oscilloscope in YT or normal mode where you can use the time base. Now connect a simple cable. This is a TDR cable. It's actually a 50 ohm cable, RG58, 1 meter length. Length has been kept at shortest. Now connect a T connector here and connect it to any of the channel of oscilloscope and try to adjust the time base and voltage, or simply if your oscilloscope has got auto set. Now what you see, a number of waveforms. You can see the frequency is roughly around 10 megahertz. Now we try to see one waveform out of 5. Now this is basically a transmitted pulse. Now at the one end of the T connector, I will connect again a RG58 cable, a 50 ohm cable whose other end is open. Now I have to trigger the oscilloscope. A little trigger level has to be adjusted. Now what you're seeing is a transmitted pulse, and this is the reflected pulse. Now here instead of all the frequencies, we are sending only one frequency, that is 10 megahertz of pulse. Now the pulsed energy is fed into this cable. Now the other end being open, we are getting a reflection. Now you can see the difference between transmitted and reflected pulse, because after reflection it has to travel through this cable. Coming and going has caused the loss, and that's why the reflected pulse is smaller. Now I connect it to a short. Now you can see in short the phase of reflected pulse has changed. Instead of being upwards, now it is coming downwards. And now if I try to terminate the cable into the characteristic impedance, that is the load being made equal to the characteristic impedance of cable, now you can see slowly I am trying to increase the resistance, and now you can see the reflection. I am losing the reflection now, reflected pulse. And now I can say it's being almost terminated. Now you can see the impedance is around 48 or 50 ohm with no reflection. That means whatever energy we have sent into the cable, it has been terminated into the characteristic impedance of cable, and no reflection is coming back. That is, no standing waves or no VSWR or minimum VSWR is there. Now this pot, this load, has got some little inductance and little capacitance, so which again cannot be nullified at high frequency as we had seen. So one can always use a perfect short. Now this is a perfect short here, and now you can see what happens in a perfect short. Now in case of perfect short, you can see the reflection is a little high because it is purely short, or almost 0 ohm with no inductive or capacitive inductance. Now it is open. Now if we put a cursor here and here, and we can measure the delta t, or the time taken by transmitted and that reflected pulse, then with the help of delta t and knowing the length of cable, which is around 4.6 meters end to end, one can find out the dielectric constant of the cable as well as the velocity of propagation inside this cable. So all we require is transmitted and reflected pulse. Similarly, we can perform the experiment for different cables. Now as you can see, we are using the short range because short range has got fast pulse. so it is used for smaller cables, whereas this long TDR range is used for long cables in range of say 50 meters or 100 meters. Now you can see with this 75 ohm cable we are getting a lot of ripples because the impedance is 75 ohm and we are feeding it with a 50 ohm impedance, so a little mismatch is there. And now you can see this is the short response, but still we are seeing a lot of ringing. And now you can see even if I try to terminate this cable at 75 ohm, we are still being able to see a little ripple, which is because of the input impedance mismatch, because we are feeding a 75 ohm cable with a 50 ohm source. So but still it is being matched roughly to 75 ohm. Now it is showing 73, so hence we can say that this is RG59 cable is 75 ohm. Now similarly I connect a lossy cable here. Again little trigger is required. Now this being a lossy cable, the reflected pulse amplitude has fallen, and now I can see the reflected pulse being gone. The impedance is here, it is showing is around 41-42. Now this method has got very good results, but the only thing is that here the cable response is being studied at 10 megahertz with the help of a pulse. Now similarly with the RG174 cable, now here you can see it's almost 45 ohm. Let us see the result with the help this TDR of this 300 ohm cable. Now you can see even if I keep the cable, very little effect is being shown because now we are operating at a low frequency of 10 megahertz. Now had we been checking the response at 300 megahertz, the coupling was causing a lot of standing waves and a lot of disturbance, but here at low frequency it is very less prevalent. So that's why we are using this cable till 50 to 100 megahertz. Now this is being terminated at 300 ohm and this is a 3-way switch. Now it is open and you can see in open you are getting a reflected pulse in same phase, and the moment I put the switch to short you can see the reflected pulse in opposite phase.